Hello, welcome to Math 170C. So this is the third quarter in our undergraduate numerical analysis sequence. And as you probably know, numerical analysis is primarily about the derivation and analysis of numerical algorithms for the solution of mathematical problems. Okay, so this is sort of derivation, sort of an analysis of numerical algorithms for the solution of mathematical problems. So I should say that this quarter draws quite heavily on the previous quarter. In particular, the quarter it's like having to do with approximation theory. So this quarter draws heavily on approximation theory. So in particular, the things you've learned about interpolation. And let me perhaps say a little bit about why it is that approximation theory plays such an important role in this quarter. And that is that many numerical algorithms which we derive can be thought of in the following way. Right, so say you have a continuous problem. Right, and what you can do is that you can try to approximate this continuous problem. So you get an approximate problem in some appropriate sense. And then you can ask whether the exact solution of the approximate problem gives you a reasonable approximation of the exact solution of the continuous problem. Okay, so there's an exact solution as well. Okay, and you can ask, to what extent these things get approximated. Okay, so the exact solution of the approximate problem compared to the exact solution of the continuous of the original problem, right? Okay, and you can ask to what extent the exact solution of the original problem is well approximated by the exact solution of the approximate problem. So let me sort of perhaps make this a little bit more sort of concrete. So imagine the problem you have is just something simple like integrating a function. All right, so you want to find integral, say, for a to b of f of x dx. From what you learned last quarter, for example, that f of x can be approximated by some sort of weighted combination of the function at a bunch of points, right? So in particular, it's like you can have what are called Lagrange polynomials, which hopefully you've seen before, ln j of x, and then multiply it by f at xj, and this is sum from j equals to say 0 to n, right? So you could potentially approximate a function by some sort of polynomial, right? And then the exact solution of the approximate problem is the integral from a to b of this sort of interpolant, right? Okay, but the f of xj is just the function evaluation of f at a bunch of points. So this is equal to the sum from j equals to 0 to n of f of xj multiplied by some integral from a to b of the Lagrange polynomial associated with that. Okay, so this you can evaluate. It's like, and that's just a weight. Then this is the function value at the point, right? And so you can ask to what extent the integral from a to b of f of x dx is approximated by this kind of weighted linear combination of the function values at a bunch of points, right? So this again is just some example of how if you know something about function approximation, replacing f of x, it's like by some sort of interpolant, for example, right? This is sort of the Lagrange interpolant, right? Then that, of course, it's like oftentimes leads to a reasonable candidate for the approximation of the original problem which you're working with. Okay, and in fact, this is of course a very systematic way of constructing numerical integration techniques based on interpolants. Okay, so I should say more generally speaking that this class is about primarily about numerical ordinary differential equations. Okay, so we're interested in the solution of initial value problems and boundary value problems using a variety of numerical methods. Again, many times these numerical methods will be based on some notion of interpolation, which you saw in the second quarter. Okay, and in fact, the error analysis that's like associated with that will then also be closely related to the error analysis you studied for these kind of interpolation methods. Okay, and as a precursor to that, it's like we'll spend a little bit of time in the first 1 or 2 weeks. It's like about how to do the quadrature problem, which is again, it's like to try to approximate integrals of functions. And the reason why that's the case, of course, is because via the fundamental theorem of calculus, right, there's a very close relationship between solutions of initial value problems and numerical integrals. Okay, numerical approximations of integrals. Okay, and also we'll look at derivatives, how to compute approximations of derivatives as well. Okay, so I should say that the course text is this book, Numerical Analysis, Mathematics of Scientific Computing. It's like by David Kincaid and Ward Cheney. So this is the third edition. Okay. So if I understand correctly, this was the text which was used in the previous quarter as well. So you'll get to continue using this in this quarter. Okay, so that's sort of again a brief overview of what the class is about, you know, it's like what role, if you will, approximation theory plays in the context of the kind of things we do. And then more generally, it's like in many of the numerical algorithms, it's like which you know, one might see in an undergraduate class in numerical analysis. Okay, so let me just stop here for now.